Hi, in this video we're going to be looking at parametric integration. So by the end of this video you should be able to answer questions like this. Stay tuned. So from before we know that the area is equal to the integration of the function of the curve, which is given by y, or f of x, and we integrate that with respect to x between x equals to a and x equals to b. Hence, because it's with respect to x. Now, if the equation is given parametrically, so this is the area where the function for y is given in terms of x. This is said to be in Cartesian form. Cartesian meaning obviously in terms it's just x and y's. So if the curve is given in a Cartesian form, we use this formula for the area. But if the curve is given in a parametric form, in other words, x is some function of t and y is some function of t, then the integration would be the same format. It would be y dx, but because both x and y depend on the variable t or the parameter t, the integration will also need to be with respect to t. So in other words, you can see if you multiply by dt here, you have to adjust it by dividing by dt. In other words, this is the formula for working out the area when the curve is given in parametric form. Just one slight adjustment will be needed. Here we see that the bounds or the limits are for the x values equals to a and x equals b. But here, because we are now integrating with respect to t, so we need to work out the corresponding value of t when x equals a and when x equals b on the top. So whatever value of t you get from x equals a goes here, and whatever value for t we get when x equals b, we put it on the top. And how to get these values obviously is looking at how x is related to t. So for when x equals a, we can work out what t needs to be, and when x equals b, you work out what t needs to be, and those will be the change in your limits. So therefore, this is the formula we need to use for parametric integration. Right, so here's the first example on parametric integration. So here we have to work out the area bounded between the curve and the x-axis between lines x equals 0 and x equals 3. When the equation given is parametrically, so x is equal to t squared and y is equal to t plus 1. We know that the area is equal to the integration of y dx. Because the equation is parametric, we have to adjust the formula for integration by dividing by dt and multiplying by dt. Okay. Now here we need to work out the corresponding t values. So I'm just going to write down t equals here just to remind ourselves that we need to obviously adjust the values here. So we don't put in x equals 0 and x equals 3 here because these are not x values, these need to be the corresponding t values. So here we have the integration of t equals. We'll put those in because it's what we need to work out. Y itself is t plus 1, so t plus 1 multiplied by dx by dt. But here we can see that x equals to t squared. So if x equals to t squared, dx by dt is equal to t. So we see this is how we work out dx dt, and we multiplied by 2t with respect to t. Let's work out what those bounds are. So this is the relationship between x and t. We can see here that when x equals to 0, 0 equals t squared will give you t equals to 0, and when x equals to 3, we have 3 equals to t squared. Therefore, t is equal to the square root of 3. Right, so here we notice that, hang on, but if you square root 3, we should get plus or minus root 3. So which one do we pick? Or to know which one to pick, either you'll be given a graph to work with, or if there's no graph, then really there should be a range for t values, because when you define a parametric equation, you have to give the range of t values that gives you the domain and range for the x and y values that defines the curve. So here, what I should have given you at the start is that the t values needs to be greater than or equal to 0. And using that now, we know that the t has to be the positive square root of 3. Okay, so if we now simplify this integration, so this is integration from t equals to 0 to t equals to root 3. So expand out the bracket, so we get 2t squared plus 2t, and we're integrating with respect to t. So perform the integration, so this becomes t to the power 3 divided by 3, so times by 2/3, plus t to the power 2 divided by 2, cancel that 2 off, between 0 and root 3. So substitute in the root 3. When you substitute in 0 for both of them, you're going to get zeros. So that's going to be 2 root 3 plus 3. So this is the area of the region that we are asked to work out. Right, so let's look at the second example on parametric equation. So here we have x equals to t bracket 1 plus t and y equals to 1 over 1 plus t. So we were asked to work out the area bounded between the curve and the x-axis. In other words, if we call this region R, the area of R, always start off with the Cartesian formula. So here we have x equals 0 to x equals to 2 of y dx. This is the Cartesian formula for the area, but we need to now adjust this for the parametric case. So the adjustment obviously will be to change the x's into t's. Here we have y dx, but now because it's parametric, we have to integrate with respect to t, so we have to then divide this by dt, and that's the adjustment needed for the parametric case. So in this example, I'm going to just work out the t values first. Now in the exam, there's a separate mark given for working out the corresponding t values. So we see that when the relationship between x and t, so x is equal to here we have t bracket 1 plus t. So when x is equal to 0, we have t and we have 1 plus t. So therefore this gives us t is either 0 or t equals to minus 1. But we see from here that t has to be positive or greater than or equal to 0. Otherwise we don't take this one, we take t equals to 0. So here we can write t equals 0. And when x equals 2, so we can have 2 equals to t bracket 1 plus t. In other words, that's going to be t plus t squared. Rewrite that as t squared plus t minus 2 equals to 0. So when you factorize this, we should get t minus 1 and t plus 2 equals 0. So therefore t is equal to 1 or t equals to minus 2. Again, our t value has to be greater than or equal to 0, so we can cross this one out. So we want t equals to 1. So you write t equals to 1 there. Just to reiterate, you do need to show this working out. This is going to be the method mark given to working out the corresponding t values. Right, so now let's work out what dx dt needs to be. We know that x equals to, if we expand the bracket, we get t plus t squared. Therefore, dx by dt is equal to 1 plus 2t. And this is what we use to substitute into our dx dt. So therefore, the area we need to work out is the integration for t equals to 0 to t equals to 1. The y we substitute with 1 over 1 plus t multiplied by dx dt. That's going to be 1 plus 2t, and we're integrating with respect to t. And just to tidy this up, we have 1 plus 2t on the top, and we have 1 plus t underneath with respect to t from 0 to 1. Okay, now let's have a look at this integration. Right, so it's a fraction to begin with. We know that it's not an ln one because if you differentiate the denominator, we get a constant, and we don't have just a constant on the top, we also have a plus a variable there. So it's not an ln one, it's a fraction, it's a top heavy fraction, and if you have a top heavy fraction, it means that the next step is to do long division to split this fraction up into little smaller terms. Right, so perform the long division. So we have 1 plus t as a divisor, so I'm just going to write it as t plus 1 divided into, so 1 plus 2t, I'm going to rewrite as 2t plus 1. So 2t divided by t is equal to 2, and multiply this out, so that gives you 2t plus 2, and then we subtract, cancels off, 1 minus 2 is minus 1. So in effect what we get here is this is equal to the integration from 0 to 1. This fraction here splits into 2 minus 1 over the same denominator as t plus 1 or 1 plus t, and we are now integrating this with respect to t. So this will give us, so if we integrate 2, we will get 2t. If we integrate minus 1 over t plus 1, will give you minus the ln of t plus 1 or 1 plus t to get it back into its previous form between 0 and 1. Here we can see that if you differentiate the denominator, we get a 1 and we have a 1 sitting on the top. So that tells us that the differential of the denominator is sitting on the top, therefore it's the ln one. Now we'll have to substitute the numbers in, so substitute 1 into here, so we get 2 minus the ln of 1, which is 2. Subtract, substitute 0, so 2 times 0 is 0. The ln of 1 plus 0 is 1. Ln of 1 is also 0. In other words, when you substitute 0 in, then both terms are going to be 0. Therefore, the area would be 2 minus ln 2. Okay, so here we worked out the exact area. Even though I haven't mentioned it here, in most cases, when you ask to work out the area, it would be to give the area in an exact form. Always give the exact answer, and if you then need to give it as a decimal, give it as a decimal. Otherwise, leave it as an exact value. Right, here's the third question on parametric integration. I'll give you a moment to try this out yourself. So pause the video, work it out, and when you're ready, press play. Okay, so here we have a curve given by a parametric equation, x equals to 1 minus a half t, and y as 2 to the power t minus 1. Show that the coordinate of point A, so if you look at the curve, it cuts the y-axis at point A. So show that the coordinate of A is 0, 3. Find the x-coordinate of point B. Well, point B is on the x-axis, so we know the y is going to be 0 to work out what the x-coordinate here. And then find the exact area of region R. So region R is the area bounded between the curve, the x-axis, and the line x equals to minus 1. And then we see it's between minus 1 and wherever the x-coordinate of B is, which we work out in part B. Alright, so let's start with question A. Show that the x-coordinate of A equals to 0, 3. Well, if you look at A, we know that the x-coordinate needs to be 0 because it's on the y-axis. So if x equals 0, look at what x is. So 0 is equal to 1 minus a half t. So in other words, a half of t is equal to 1. Well, that gives you t is equal to 2. So at point A, what we know is that the t coordinate here is equal to 2. So when t is 2, it gives you, when t is 2, that gives you x equals to 0. So if we now substitute t equals 0 into the y coordinate, or the y equation, y is equal to 2 to the power t minus 1. So in this case, with 2 to the power 2 minus 1, we get 4 minus 1, which is equal to 3. Hence, point A has coordinate 0. When x equals 0, we get a y coordinate of 3. So here we have shown that when x equals 0, t needs to be 2. And that same value of t gives you y value of 3, so we get 0, 3. This working out here is the showing part for this coordinate. In part B, find the x-coordinate of point B. Well, point B is on the x-axis, so we know that y needs to be, so here I will write down at point B, we know that y needs to be 0. Okay, if y equals 0, the equation of y is 2 to the power t minus 1 and needs to be 0. In other words, 2 to the power t equals to 1. So ln both sides, so ln of 2 to the power t equals to the ln of 1, or here we'll have t ln 2 equals to ln of 1 is 0. In other words, we get t equals to 0. So we now substitute that into the x coordinate. X is equal to 1 minus a half t. We're going to substitute in t equals to 0. So that gives you x is equal to 1. So therefore at point B, the x coordinate is equal to 1. So here, just going to write down here, x is equal to 1. Just going to note that when x equals 1 here we worked out that the t value here, the t value at point B is equal to 0. So t is 0 at this point. I'm just going to rub this all off so I can have more space for working out part C. So the exact area of R would be the integration from x equals to minus 1 to x equals to 1 of y dx, and adjust for parametric case, so t equals y dx gets adjusted to dt over dt. So that's the adjustment into parametric case. If we work out the t values now, so we know that we need to work out the t value here, what the t value is. We already worked out the t value here is 0, so obviously the top here we can substitute in 0 for the top. So just to work it out here, when here we know that when x equals to minus 1, or 1 minus a half t equals to minus 1, so we'll have 2 equals to a half t, in other words t is equal to 4. So our t value here is equal to 4. We're now going from 4 to 0. Y is 2 to the power t minus 1 multiplied by dx by dt, or x equals to 1 minus a half t dx by dt is equal to minus a half. So here we'll have minus a half dt. To tidy this up, what we have is minus, so integration from 4 to 0, minus a half, bracket 2 to the power t minus 1 dt. Now I'm going to show you a slight trick here. The overall coefficient is minus a half. What we're allowed to do is we're allowed to pull out the constant coefficient outside the integration sign. So this is minus a half. We can write it outside the integration and rub it off from the inside. And the second thing is, see this minus sign. This minus sign can be absorbed into the integration. What the effect it has on the integration is that it swaps the limits around. Okay, so we can deal with a minus by swapping the bounds around. So what we now have is half times the integration. Rather than going from 4 to 0, we're going to go from 0 to 4 now, because the minus sign has been used by swapping those bounds around. And we are integrating 2 to the power t minus 1 with respect to t. Okay, all that need for us is now to perform the integration and plug in the bounds. Okay, so we have a half on the outside. Right, so integrate 2 to the power t. Well, ask yourself what differentiates into 2 to the power t. Well, it's an exponential function. We know that an exponential function differentiates into an exponential function. But let's test that theory. So if we were to differentiate 2 to the power t, we will get 2 to the power t, but then we have to multiply by the ln of the base number, which is ln2. Okay? Compare this with the 2 to the power t. Well, we don't have a ln2 in our expression here, so which means that we have to adjust this to get rid of that. We have to multiply by 1 over the ln of 2. Therefore, this needs to be multiplied by 1 over ln2. So, in other words, when we integrate 2 to the power t, we get 1 over ln2 times by 2 to the power t. And then we integrate -1, it gives you minus t, and the bounds are from 0 to 4. Substitute in 4 here, so we have 1 over ln2 multiplied by 2 to the power 4. 2 to the power 4 is 2 times 2 is 4, so that gives you 16. Minus 4 goes in, so we get -4, close bracket. So minus a half, open up another bracket. So 0 goes in, so we have 1 over ln2. 2 to the power 0 is 1, so we just have 1 over ln2 remaining here, minus 0, so it's 0, so close bracket there. If we now just factorize the half out altogether, we have 16 over ln2 minus 1 over ln2 minus 4. Therefore, the final answer here we have 16 over ln2 minus 1 over ln2, so that should give us 15 over ln2. Obviously, we'll multiply by half, so it's going to be 15 over 2 ln2, and then minus 4 times a half is equal to minus 2, and this is the area that we asked to work out. I hope you have enjoyed this lesson, so keep practicing, and I'll see you in the next video.